Hello, so today I'm going over the homework 4 for the class EEDG 6370 offered in the fall of 2024 at UTD. And for this homework, the goal was to take a design, find the critical path, and then change the location of some of the registers to see what would happen as a result. So to start off, we're going to look at the original compilation with no changes whatsoever. And what you can see here in the fitter report, you can see that it uses a total of 49 ALMs, 84 ALUTs, has 241 IO pins. It uses no BRAM and no PLLs. And registers, it has a total of 77. So we're going to go to the timing analyzer. So I'm going to go through here to pull up the timing analyzer. So let's look at the Fmax summary. And the maximum frequency for this design is going to be 276.01 megahertz. And now if we look at the critical paths, if we look at the 5 most critical paths, what you can see right here is it has a slack of about 16.377 nanoseconds, and it's most critical path. And over here you can see the delays of about 2.47 nanoseconds. Now in the chip planner, you can see that the critical path that we're going to look at is down here. And you can see this path right here, from here, going up, and then going down. That is the most critical path. And what we're going to do is we're going to change this critical path and see what happens as a result. So what I want to do is make a split window. And for one of them, I'm going to put it down in this corner. So what I would do is I would take this, I would hold this, and then I would drag it down to here. And for the other one, I would take it and drag it up here to the top right corner. For example, I would take this and then I'd move it to right here. But I've already done this before, and so I'm just going to load the constraint and show you that. Now, looking at the constraints file, if I scroll all the way down to the bottom, you can see I set the location before. Now I'm going to toggle the comments, and I'm going to recompile. And what this will do is when it is placing the registers, it'll place it where I designated. Okay, so now that the compilation is complete, we're going to look at the resource summary again. And now in this resource summary, what we can see right here is we use a total of 50 LMs. We use a total of 84 LUTs. We use 82 registers. And we have 241 IO pins still, no block RAM and no PLOs. And now the new Fmax has changed to 149.3 megahertz. And if we look at the critical paths, the critical paths have a lot less slack now. The data delay has about doubled, just over doubled. And if we look at this in the chip planner, what you can see is that the design or the signals go all the way from the top left to the bottom left, and it appears that maybe the adder is right here. And also if we look at the other critical paths, you can see that it is also from the top to the bottom, because these paths are all combined. It's all part of the counter. So if you move part of it, all of it's going to move together. And so now what we're going to look at is what happens if we change the frequency of the clock that is driving the design. So we're going to uncomment this. We're going to comment these lines. We're changing from 50 megahertz to 500 megahertz. And I'm going to get rid of the location constraints. Save that, save this. And I'll compile it again and be right back. So now the 500 megahertz compilation has completed. And we're going to look at the fitter. So you can see in the fitter that it uses 49 ALMs. It uses 84 ALUTs. It uses 79 registers. And it uses 241 IO pins, and everything else, BRAM and PLLs is 0. And now we're going to look at the timing analyzer. And we're going to report the Fmax. So what you can see is that the Fmax for the design is 275.48 megahertz, which is similar to what it was before we changed from 50 megahertz to 500 megahertz. But as you know, 275 megahertz is a lot less than 500 megahertz, so there will be issues with this design. And now if we report the timing for the 5 most critical paths, we'll see what happens. And here you can see that the data delay is still 2.4 nanoseconds, but now at 500 megahertz, it has negative slack. So for the most critical path, you can see it has a negative slack of 1.63 nanoseconds. And so this design is not going to work properly. It is going to be very unpredictable. And with this unpredictability, you are not going to really have a functioning design. Now, the reason for this is the infrastructure of the FPGA does not really support this kind of speeds for a design that is using, say, an adder. Now, the FPGA may be able to do this if all you're doing is moving data around, but in a design where you are actually performing operations, it's just not going to be able to do it. So this has been Homework 4. Thank you for watching.